Okay, hello again. And in this section of this screencast, I want to talk about internal reliability. Internal reliability is an indication of how well items or tasks in an instrument work together to measure the same thing. For this reason, some scholars have referred to internal reliability as homogeneity, but I personally don't think that having internal reliability or having a high internal reliability is an indication that you have homogeneity. Because to me, a homogeneous group of items basically measure more or less the same construct. But having a high correlation between items, meaning that the fact that they work together and as a result they have a high correlation, does not necessarily mean that they are measuring the same construct. They could be having high correlations for different reasons. Therefore, scores and performances on similar items are consistently related in an instrument which has high internal reliability for scores or high internal consistency. A reliability estimate will be unique to that sample of participants at that particular occasion. And this is a very important point. So reliability estimate is not about the test. Reliability estimate is about the sample of participants, specifically about their test scores. And on that particular occasion, it's because if you administer a test of, let's say, reading comprehension, grammar, vocabulary skills, and so on, and if you get a reliability of 0.6, let's say, on occasion 1. It does not necessarily mean that if you administered the same test again to the same group of people, you would get exactly the same reliability statistic. A lot of things can happen between time 1 and time 2. And therefore, this reliability index is an indication of the consistency of the scores for that particular occasion and for that particular group of people, not for the test itself. And this is something that I have sometimes seen in papers where the authors argue or claim that the instrument was reliable because, for example, Cronbach's alpha was equal to 0.7, 0.8, and so on. And that's like a common error that has been prevalent in quite a number of papers that I have read. The next thing is that consistency of responses across test items that measure the same construct is the center of attention. In other words, we need to make sure that the instrument is measuring the same construct. All of the items must load on one specific construct or one specific factor, in other words. So we will be able to claim that the reliability statistic that we have calculated is applicable to that specific construct that the test is measuring and no other constructs. In fact, this idea of unidimensionality, as I will say in a few minutes later, is one of the assumptions of many of these internal reliability statistics. Okay, so the internal consistency or internal reliability index that we're going to discuss today is Cronbach's alpha, although there are many other types, such as McDonald's omega, etc. Cronbach's alpha is an estimate of internal consistency, as I mentioned, and it measures how closely a set of items are related as a group. In other words, how closely they're correlating with each other. So the higher the correlation, the higher the Cronbach's alpha value, generally speaking. The range of Cronbach's alpha is between 0, which is no consistency at all, to 1, which is perfect consistency. Of course, Cronbach's alpha of 1 is not necessarily desirable. Something above 0.9, but less than 1 would be more desirable. As I mentioned, Cronbach's alpha or certain reliability statistics are derived from the classical test theory, which can be written in this way as well. It's assumed that under classical test theory, a true score is equal to observed score minus error. So based on this, we can estimate how much of the variance that we observe in the data is attributed to the true score or the true ability that you are measuring, and how much of it is attributed to error. For example, if the alpha coefficient that we estimate is equal to 0.9, which is very high, it means that 90% of the variance in the observed test scores is due to the true score, or the true ability that we are measuring, which reflects the construct of interest. Conversely, the remaining 10%, which is not explained by the true score, is due to the measurement error, which includes factors which are random. I want to stress this word. It's random. They have to be random, not systematic. Random errors, including respondents' misunderstandings, random respondent misunderstanding. Item ambiguities, which are again random, they're not systematic, and the test has not been inflicted by a large number of items that have been written ambiguously. In this case, we can claim that the part of the variance that is not explained by the true score or is not attributed to the true score is basically measurement error. It's important to note that a higher Cronbach's alpha indicates higher internal consistency of the data, as I mentioned before. It's not an indication of validity. It's not an indication that the test is reliable. It's just an indication that the data that we have collected have internal consistency. And so we shouldn't read too much into an index like Cronbach's alpha. Okay, so the question is, how is Cronbach's alpha calculated, and what can we learn about the way that this coefficient is calculated that can help us to improve internal consistency of our measures? So first of all, how is it calculated? It's calculated using several formulas. The one that I prefer and is my favorite is this one. Alpha, this one right here. Alpha is equal to n, which is number of items, multiplied by average covariance or average correlation of items, divided by average variance of each item plus number of items n minus 1 times the average covariance or average correlation. It doesn't matter which one you use. Both of them work, average correlation and average covariance. And if you estimate both of them, you will see that they are more or less the same. So from this formula, we learn that basically the correlation between items, and as a result their average or the mean, is very important, because it's not only in the numerator but also in the denominator. If the numerator of this formula is large, meaning that if the correlations between these between the items are high, the numerator is large, and as a result the fraction which gives us the Cronbach's alpha value will be larger. But on the other hand, if this average covariance between item pairs is small compared with the average variance in each item, then we will be looking at a problem in terms of internal consistency, meaning that there is not enough variance in common between item pairs, and the idiosyncratic or item specific variance is larger than variance in common between them, and this would result in a lower Cronbach's alpha value. So if we want to have a higher correlation Cronbach's alpha value, we need to include items that have higher correlations, relatively lower variances compared with correlations, not necessarily low variance, but relative to the correlations between items, the variances are smaller, and a larger number of items always helps, because you can see that n is in the numerator and n minus 1 is in the denominator. In this case, If the n is larger, we will have a higher chance to get a higher Cronbach's alpha value. So to answer the question, let me just wrap it up for you. Higher correlations between items and a larger sample size in terms of the items, and relatively lower variances of items compared with correlations between item pairs can help us get a higher Cronbach's alpha. One more thing, when we say correlations, if there is an item that has a negative correlation with the rest of the items, that item must either be removed or it must be reverse coded, because negative correlations are very detrimental to the integrity of Cronbach's alpha. I'd like to add a few more recommendations for you just in case you're curious how else we can improve Cronbach's alpha. If you have a narrow construct which is measured by just few items, generally speaking, you may get a low Cronbach's alpha value, which is not good. If you want to get a higher Cronbach's alpha indicating higher internal consistency, it's a good idea to get a broad construct, construct that has got several subdimensions which are closely correlated with each other, not subdimensions that are not closely correlated. I must stress that. And each of these subdimensions or components of that construct are measured by several items, not just by 2 or 3. In this case, you can assume that you will get a high Cronbach's alpha value, and as a result, the amount of error that is affecting your test scores or your data in general will be much lower compared with the first scenario that I just mentioned. Cronbach's alpha, as I mentioned, depends on average item correlations. Therefore, if you create a histogram of item correlations like this, if this histogram is something like a normal distribution as this one, chances are that you will get a higher Cronbach's alpha coefficient. But if the histogram is skewed like this or skewed this way, that is positively and negatively, then chances are that you'll get a lower Cronbach's alpha value. In addition, low item discrimination is also detrimental to Cronbach's alpha value, because low item discrimination indicates that the item does not differentiate between people who are high ability or low ability, and this, as a result, can lead to having a low correlation between the rest of the items which have discriminated between high ability and lower ability, and the outcome of that will be a lower Cronbach's alpha, because that affects the average correlation, which is integral to calculating Cronbach's alpha. In addition, there are factors that can affect Cronbach's alpha, and they're more kind of illusory and kind of difficult to measure and investigate, such as correlated measurement errors. And this is something that I have discussed in other videos, including those where I talk about Rush analysis, the concept of local independence, and also item response theory models. Please watch those videos if you're interested. Multidimensionality is another detrimental factor to Cronbach's alpha. If your instrument is multidimensional, chances are that the correlation between the items will be low, and that simply affects your Cronbach's alpha adversely. Unequal factor loadings, it's a technical term. It's also